So let's go ahead. Yeah, first of all, I'd like to thank everyone who's joining us today. Welcome to the CNCJ August meetup event. My name is Harry Lee. I'm the organizer of CNCJ. Today we've got Lukonde Mwila. We're actually quite honored to have him joining us. He'll be sharing with us scaling with Karpenter, which is awesome. I think it's also, I've never heard of Karpenter before, so it's a lot of learning we'll be doing today. Just a few housekeeping items aside. The session is scheduled for 1 hour. We've given this talk a technicality rating of 3 out of 4. So that means this talk is quite technical and you'll be hearing quite a bit of Kubernetes jargon, so strap in. Questions are always welcome, but please keep them on topic. We want to make the session as interactive as possible. So you'll get a chance to speak. You can unmute yourself when you want to ask a question, but you can also ask your questions in the chat panel. So this session is being recorded and moderated, so please be respectful towards the speaker and your fellow participants. You will be kicked out if you do not abide by our code of conduct. And this session will be available on YouTube under the official CNCF community YouTube channel over the next 2 days. And with that, I'll hand it over to Luke, who will be telling us about Karpenter. Luke, the floor is yours.
Awesome. Thanks a lot, Harry. And hello, everyone. Really wish I could see you, but I'll definitely make do. Either way, I'm excited to have this opportunity and I appreciate you making time. As you can see, I'm going to be speaking about scaling Kubernetes with Karpenter, which is an open source tool, and more specifically, how you can meet advanced scheduling requirements such as inter-pod affinity and volume topology awareness. And if you're not sure what those concepts actually are, that's totally fine. We'll be able to delve into that a little bit later. But just a quick intro. Well, actually not so quick anymore. I'm told it's nice to share a bit of the speaker's journey or story. So I'll elaborate on that, and you're more than welcome to ask me questions at the end as well. So as Harry said, my name is Lukonde Mwila. A lot of people call me Luke as well. Back in the day, way back, some people called me Skywalker because I'm a big Star Wars fan. But here's an interesting point, though. Luke Skywalker is the least of my favorite Jedis. So don't call me Luke Skywalker. All right, and so I'm a principal technical evangelist at SUSE, and I know that is such a mouthful. Whenever people ask me my job title, I feel like I need a glass of water right after that because it's just so wordy. In addition to that, I'm an AWS hero and a HashiCorp ambassador. Not many people know what a principal technical evangelist actually is. It's essentially just another fancy term for developer advocacy. Developer advocates are engineers who are heavily involved in the developer community and helping the developer community understand and adopt and make the best use of certain technologies, as well as hearing from the developer community on things that could be improved on particular tools or products. So it's something that I'm really passionate about because I love engaging with people and especially helping out around certain technologies. At the moment, my job is specifically focused on the cloud native space. But as you can see, being an AWS hero, I'm also a big fan of the AWS landscape. And so I love to help other people around the different components and navigating the AWS space, as well as using HashiCorp's tools, which I'm a big fan of, especially Terraform. More specifically to my career background, I started off in application development, full stack development with PHP, and then transitioned to building out a lot of front-end applications. So I was more of a front-end developer after going from full stack, focused on for quite some time, and it was great. I worked a lot with React.js. So if any of you have ever watched some of my videos or seen some of my example applications and tutorials or technical articles, you'll see that either React or Node.js are my go-to languages. That's because of my background in working with those technologies on different applications. After doing that for some time, I then transitioned into the consulting space, which was a lot of fun. And I was working in the financial services sector, working on larger enterprise systems and specifically cloud solution architecture, implementation of those same architectures that I was a part of designing, as well as administrating Kubernetes. And I also had the chance to work with Harry, which was really cool. So I certainly missed those days, but very, very thankful for the fact that I get to do developer advocacy on a professional basis. And the reason I say professional basis is because even before I got into this particular role, I was heavily invested in terms of making time to write technical articles and create different resources to make life easier for other software engineers. And that was essentially born out of personal frustrations that I faced. And I'm sure everyone on this call could probably attest to that. You're working through some tutorial because of a problem that you're facing at work. And so you're trying to figure it out, and then you come across different things online, and sometimes those don't necessarily translate to your context well enough, or there aren't enough good examples. And so it was a really good, if I could call it, training ground or opportunity, just to make time to start building out resources that I thought would be helpful for others. And I've been passionate about that ever since. So I'm very excited that I got to do this on a professional basis. If you have any questions around that, please feel free to ask me at the end as well. Okay, so let's see what we have lined up for today. Whoops. We have okay, that's not good. We've got a 404 error. Well, I'm just kidding. All right, sorry, I had to get a dad joke out. All right, so I'm actually trying out something new. A friend of mine said to me, you want to keep people on their toes, build the suspense, so forget the agenda, scrap it, and then the dad side of me got the better of me, and I thought I'd throw a little dad joke in there. So there's the 404 error. So you just have to stay on your toes and stay along for the ride, which I hope everyone will, and hopefully we'll even have more people joining on the session. So let's talk about scaling Kubernetes in general. So this is a really popular topic for obvious reasons. And when you think about Kubernetes, some of the things that come to mind are its declarative model and its self-healing capabilities, which are standout features. It's this robust and intelligent system, complex nonetheless, but how you can scale with Kubernetes is another big feature. It's one of the reasons one of the popular case studies of Kubernetes would be Pokemon Go. A lot of people talk about how Pokemon Go scaled to handle the traffic of millions of users around the world. And that's one of the good case studies of what Kubernetes can do. But obviously, we want to figure out how we can actually achieve that. And Kubernetes does provide good mechanisms for you to scale both your workloads and the cluster. And so I'm going to start off by talking a little bit about those two components before focusing more on the latter, which is what this session is focused on. So when it comes to scaling your workloads, you think about, there are different types of scenarios that could lead to this. For example, you could be working with different types of applications. So you'll see this diagram over here has Node.js apps, which are typically very light. We've got Spring Boots, which are more robust and usually a little bit heavier. And then we've got Redis as well. And so this is just to depict the idea of you have unrelated applications, or maybe related in some ways, depending on your particular solution, running on the same Kubernetes cluster. And they might have different resource requirements, which could potentially lead to you scaling. And in addition to that, they could also be experiencing different levels of traffic. You might find that the Java application over here has a high level of traffic throughout the day, and the Node.js application maybe just a couple of times in the morning, and usually late in the day as well. You could even have a few jobs that are being fired off. So it will vary, from unrelated workloads to related workloads running on your cluster. They have different resource requirements, and even from a network traffic perspective, they will have variances in that particular regard as well. But something that will remain constant is that whatever the case may be, your concern is that there's no compromise in the network traffic requests being met by the different workloads running on your Kubernetes cluster. You don't want any compromise in that regard, or any kind of degradation for the clients in the cluster or any end users outside of the cluster as well. And so that's where the idea of scaling comes in. We want elasticity, whether that elasticity is brought about by scaling our cluster due to workloads that have higher resource requirements, or because we have additional Kubernetes or additional applications that have to be added to our cluster. And I'm going to speak a little bit about that now. So let's start off by talking about the workloads. So thankfully, we've got some native Kubernetes resources like the virtual pod autoscaler and the horizontal pod autoscaler, which allow us to meet these particular requirements in the case of our workloads. So horizontal pod autoscaler is useful if you want to scale, if you want to be able to scale your applications out, and the vertical pod autoscaler is useful if you want to scale your applications up. I'm going to delve into just one of them. I'm going to use the horizontal pod autoscaler as an example. So the horizontal pod autoscaler is reliant on receiving metrics from the metric server, and it's going to get information on the utilization of pods that you have running inside of your cluster. And based on that information and configurations that you put in place, for example, certain thresholds, and if those thresholds get hit, then you want to be able to scale up. And so the horizontal pod autoscaler will then go to work, and it's going to modify the desired state on of your replicas in a particular deployment resource. The horizontal pod autoscaler doesn't itself actually create new pods. It simply modifies the desired state. And the deployment controller is then going to go to work and essentially act on the new desired state to make sure that the live state matches up with that. And I have a manifest file over here that I've zoomed into just to make that a little bit clearer. You see that we've got a couple of dotted white blocks that are bordering the spec section of this manifest file, and you'll see the area where it says replicas 2. So that's what the horizontal pod autoscaler is actually going to be manipulating, and it's going to change that in order to match the traffic demand that is coming through for that particular workload that you have. Again, this is all based on metrics that it's receiving from the metric server, as well as configurations that you put in place on how it should respond to those specific configs. All right, and so what we have on the left-hand side is what you might start off with. You got a deployment, and it could be for 2 replicas, which is a little bit weird. I know the norm is that you'll usually have 3, so I hope no one is really bothered by that. But yeah, so 3 is usually the minimum for best practices, if I recall. And then on the right-hand side is a situation in which our horizontal pod autoscaler has gone to work, it's updated the desired state, and then the deployment has responded to that and spun up new pod instances. And so this is great in terms of scaling our workloads, but then we have to ask the question, what happens when our underlying infrastructure or the underlying compute resources are fully taken up or exhausted? We hit the ceiling. What do we do then? Well, the obvious response is we add more compute resources, right? Now let's turn our attention to another situation in which our cluster could end up scaling. And I referred to this earlier as well. So you'll see we've got the same diagram as earlier, just added a few more pretty icons to it. And so we've got app A, B, and that's so funny. We've got app A, B, and D, but we don't have C. Well, anyway, we'll pretend that C was decommissioned. Okay, so and so let's say that these 3 applications that exist on the cluster at this point in time have completely used up the underlying resources, right, for our cluster at this point in time. But then we want to add more applications to our cluster. So you'll see there we've got app E, F, and G. We've got Nginx, we've got Prometheus, and we've got Flagger that we want to deploy to our cluster. So this is the second scenario. In the first scenario, we were working with one application that needed to be scaled out based on its utilization because of increased traffic demand. But this is another situation that could result in you having to scale your Kubernetes cluster. We hit the ceiling before, but this is another way that you can hit the ceiling if you've maxed out the resources for your existing infrastructure for your cluster. And so you'll find that you have applications that you can't deploy until you've beefed up your compute resources. So once again, the answer to that question would be we add to our compute resources. But then when it comes to the topic of adding compute resources to our Kubernetes cluster, yes, we definitely want this done in an automated way. That's a bit of a no-brainer. And granted, there may be situations in which you have a really small cluster and maybe there's room for an operator to be able to just modify that in the console to, increase the desired and the max number of compute resources for a particular cluster. But in an optimal way, we definitely want to be able to automate the entire process. But there are a couple of things that we want to consider apart from just having things automated. For example, you could automate the process of just adding the same type of, by the way, I'll refer to AWS a lot because Karpenter at the moment only supports the AWS context, but there's a big invitation for people to contribute to that. It's designed to actually go beyond just the AWS context. So bear with me if I use that AWS jargon. And so let's say we have a cluster that has a single node group with T3 medium EC2 instances. We don't want a situation where we just keep adding more of those T3 medium EC2 instances. what if we end up over provisioning or under provisioning? That can result in an inefficient model, essentially, of having all of the right kinds of compute resources that we need for our workloads. And so Karpenter, in many ways, is a response to those kinds of issues. It's firstly, it is an open source tool, as I've already mentioned. It was built with AWS, and I'd encourage you to join the community. There's a Slack channel in the Kubernetes workspace, so you can see all that's going on in terms of the activity and building out Karpenter. And in addition to that, you can engage with other people who are trying to, make the best use of it. And so Karpenter is set apart by the fact that it takes into consideration the requirements of your pods. It takes a look at what's actually needed by that pod, from the resource requirements to any scheduling constraints. And we're going to delve a little deeper into that. And bearing these things, quote unquote, in mind, Karpenter will then communicate directly with EC2 in order to provision the exact compute resources that are needed, no more, no less. So this takes away the challenge of, or the administration rather, of having to create multiple node groups that are created for specific workloads. For example, if you have a large applications or compute intensive applications or memory intensive applications, sometimes you might end up having to create different node groups that meet those specific workloads requirements. And that's how you're going to manage your scaling, but it's not a very efficient model. Instead, you want to take away essentially do away with the whole process of being constrained by a specific node group, and instead, just have that direct interaction with EC2 and being able to modify the instances for your particular node group based on the workloads. So instead of just adding additional T3 medium EC2 instances, you could have a situation in which Karpenter would look at what's required by those pods, and it might say, all right, I'm actually going to get rid of the 4 existing T3 medium EC2 instances, and I'll get rid of 3 of the 4. We'll keep 1, and then I think, an M4 instance, for example, will be able to match the requirements of all the other workloads that could have been added to the cluster, or if a particular application is scaled out. So that's really what sets it apart. It takes into great consideration what's going on with the actual workloads, what is needed, and based on that is how it's going to provision or add compute resources to your cluster. And it also works out as a very cost-effective model. So I'm not going to delve too much into the introductory components or pieces of Karpenter, because I want to focus more on how it can help you with advanced scheduling requirements. But you can definitely ask your questions at the end, and I'll be happy to also refer you to other good resources out there. Okay, so this is just a little bit of what I already mentioned about Karpenter being an open source cluster autoscaler built with the AWS team. And as I said, it's designed to work with any Kubernetes cluster. At this point in time, it's just with AWS. It doesn't have to be an EKS cluster, even though I will be working with an EKS cluster later on in my demo. You can also provision a custom cluster with EC2 instances, and it will be able to work just as fine. And we're hoping to see, the community is hoping to see more contributions for other cloud providers as well. So maybe that's a way that you can definitely get involved. All right, so let's start off by talking about inter-pod affinity. And this is a really helpful feature because there are times when you want to be able to apply additional constraints, scheduling constraints, to your workloads. And those constraints could be based on how you want your pods to be able to relate to each other, whether you want there to be an affinity towards each other for particular pods, or if you want pods to be repelling each other. And this is going to be across the topology of your clusters architecture, so across the different nodes. And this is very useful for different use cases, which I'll jump into. For those of you who are familiar with node affinity, it's a very similar concept as well. And so the same rules that you would apply to node affinity in terms of a hard and a soft approach, you would be applying those same rules to interpod affinity as well. So you'll see over there, required during scheduling, ignored during execution. So this is for a strict approach in terms of the scheduler knowing how serious to take the the scheduling constraints that you've put in place for a particular workload or those particular pods. And a preferred approach, as the name implies, is that it's not going to be a hard or strict approach. It's going to be more of a soft one. And so the scheduler is essentially going to be working with these particular constraints and knowing where it should be placing your nodes across your different cluster, or whilst considering also the overall topology architecture. And I'll have diagrams as well to help paint the picture a little bit better. So inter-pod affinity consists of both pod affinity and pod anti-affinity. You might have heard me mention how you might want some pods drawn close to each other or attracted to each other for to be when they're being scheduled on particular nodes or in a particular availability zone. And similarly, they could be repelled across the cluster, across different nodes. So let's start off by talking about pod affinity. And this rule or constraint essentially informs the scheduler to match pods that relate to each other, and it's going to be based on their labels. And so let's say you've already got an Nginx application and a React.js application, and or rather, let's say you've got the Nginx application that's already been deployed, and you attach certain labels to that particular application, and then you also want to deploy a React.js application, and you want Nginx to be proxying the traffic through to React.js. In the case that you want them to be perhaps deployed on the same host or in the same availability zone, you could then apply an affinity rule, and they would then have matching labels. And so when you would apply these particular affinity rules, and the scheduler would be aware of that. So after you've deployed the Nginx application, and let's say now you're deploying the React application, it's going to be able to search the nodes to essentially see, I see that there's a workload that exists at the moment that has this particular label and matches this one. Therefore, I'm going to schedule it to that particular node or that particular availability zone in order to meet that affinity rule. Okay, so this diagram might help paint the picture a little bit better. And so in this case, you'll see right at the top, we've got on the left-hand side, we've got a pod with I'm pretty sure that's orange or a dark yellow with an orange square background. And on the right-hand side, we've got the green square. And so these are two different pods representing two different applications, right? And so the topology key in this case, which is what we want our affinity rule to be based on, is AZ representing an availability zone. And so this rule or this constraint is essentially telling the scheduler that I want these pods to be in close proximity or to have an affinity towards each other in the same availability zone. They might be placed on the same node. That's not the constraint in this case. The constraint is that they have to be in the same availability zone. So whether they end up on the same node or not is not so much of a biggie. It's more about the availability zone. So if you now pay attention to the blue block at the bottom over there, you'll see we've got three different nodes in our cluster. And I want you to pay specific attention to the one on the left and the one in the middle. So each of these nodes has been provisioned in a certain availability zone. The one on the left and the one in the middle are both in EU West 1A. So that's in Ireland. So that's the EU West 1A availability zone. And then EU West 1B has the third node, the one which is on the far right over there. And so this means that the scheduler would essentially look at these particular constraints and make sure that the pods that match that same label would essentially be placed in that same AZ. So you'll see that in that diagram, we've got the green blocks, the pods with the green backgrounds with the pods that have the orange or dark yellow backgrounds as well. And so that's one of the ways that you would essentially meet this particular affinity rule. And the reason for this, as I mentioned, I'd speak a bit about use cases, is you might want to reduce things like network latency or increase performance for particular applications that might be closely related. And so something like this would be a very helpful use case for a situation like this. All right, so pod anti-affinity is essentially the contrast of pod affinity. It's a rule that allows you to prevent certain pods from running on the same node if the matching label or criteria are met. And so I've got another diagram here to help depict that. So same concept, and in this case, I am using the same topology key in terms of an availability zone. So if you pay attention to the cluster block right at the bottom, you'll see that in this situation, there are no pods that have there are no green or orange pods that have been scheduled on the same node or in the same availability zone. So you'll see that we've only got purple and orange together in EU West 1A because of that particular affinity rule. Now, just remember that I did mention that you can apply the level of strictness that you want, whether required or preferred. And if it's required, then the scheduler will do its best to make sure that those particular requirements are met. And in the case that if it's preferred, then you might see a little bit of mixing and matching. For the most part, it'll meet the rule, but you'll see that it won't be as strict as a required approach, right? So now you might be wondering, okay, so how exactly does Karpenter come into this? Oh, before we move over to volume topology awareness. So Karpenter comes into play in the sense that if you think back to what I was mentioning about the different workload requirements that you may have. So these workloads are ending up on your cluster, and they've got different requirements from a resource perspective, but also from the perspective of some scheduling constraints like the ones that we're focusing on right now. And so when these get deployed and they end up in a pending state, Karpenter is essentially watching out for that or keeping an eye out for that. And when it is providing additional compute resources to your cluster, it's also going to keep in mind the scheduling constraints. So for example, let's keep with the same anti-affinity rule in the same diagram that we have here. Let's say we had 20 replicas of the green pod, right? So 20 replicas of the green pod, and we'll keep it as 3 and 3 for the purple and the orange. So previously, we might have had 2 nodes, and those 2 nodes were able to meet essentially to match all the requirements for those particular workloads. But then we want to scale up our application. We are scaling it, the green pods from, let's say, 3 to 20. All right. And so we get to that 20. And so when Karpenter is seeing what's happening, it's aware that we need to beef up our compute resources. It'll provision a node, or an EC2 instance that meets the scheduling requirements as well as the resource requirements. So in this case, because we're talking about 20 pods, it could be a really big EC2 instance, and it'll make sure that it gets provisioned in EU West 1B to make sure that it's still meeting that pod anti-affinity rule. And the pod affinity rule would work the exact same way in terms of how Karpenter will work in conjunction with the scheduler and the constraints that have been put in place. So this is really useful because you don't want a situation in which you've got scheduling constraints that you're applying to your workloads, and at the same time, you don't want your cluster auto scaling strategy to be compromised in that particular way. You want it to be able to complement what you're doing in terms of the constraints that you're adding. And as you can imagine, this can easily end up being something that is not done in a cost-effective way or in an efficient way. Imagine having to manually provision node groups and taking care of all the different constraints in a manual process yourself to make sure they get added to certain availability zones, or trying to provision the right EC2 instance or EC2 instances for certain workloads. But this can get taken care of in an automatic way while still considering all the different requirements for your pods. And that's something that Karpenter does. So really shines in this particular sense. And I'll also demonstrate this right at the end. All right, so what on earth am I talking about here when I say the dark past? So we're about to now transition into the volume topology awareness section. And before we get into that, there is something that I think is really important to understand, and that's how scheduling of pods worked in conjunction with dynamic provisioning of volumes. In the past, these processes were independent. And the reason why I'm saying this is the dark past is because, as you can imagine, this can introduce a number of challenges. It basically brings in unreliability and unpredictability because you might have because if you're going with dynamic provisioning, that means you create your persistence volume claim, which will dynamically create the volume. But if that happens in a certain availability zone, let's say availability zone A, and the scheduler is looking at different nodes and it says, oh, there's a node, let me schedule these pods to this particular node. But it so happens that that node is in availability zone B. Well, your pods aren't going to start. And some of you might have run into those issues. So that means that, and the reason for that is because those pods are reliant on volumes that they're not able to tap into. So this is especially useful for stateful workloads. So what you want is essentially to make sure that this is something that happens in conjunction, that there's an awareness basically of where the relevant topology resources are taken into consideration when scheduling certain pods. And that's what volume topology awareness brought into play. So topology awareness ensures that the pods are placed on nodes that actually meet their topology requirements. So in this case, we're talking about storage volumes. And the goal is to provide alignment between topology resources and your workload. So basically solving that problem that existed before when scheduling of pods and the dynamic provisioning of volumes were independent processes. So once again, we have to be thinking, great, this is good for our workloads. And because the topic of today is around scaling, how does Karpenter come into play? Because at some point, especially for large stateful workloads, and that's something that I'm going to demonstrate as well, this could easily max out the existing resources that we have for our EC2 instances or our nodes in our cluster. And so we want a situation in which when there's more dynamic provisioning taking place and more compute resources are being added, it still supports the same volume topology awareness as well, which is a really important feature. So you'll see right at the bottom over there, I have that equation. The topology manager, which is a component of the kubelet, works very well with the scheduler and with Karpenter to give you an optimized scaling of your stateful workloads. Right, and just as before, I do have a diagram here that will help make this a little bit easier for those of you that prefer to have some kind of graphic in front of you. I know I'm definitely that way. So we've got our persistent volume claim, which obviously is what we're going to use for our stateful workload, and that's going to dynamically create a persistent volume for us. And under the hood, in the AWS context, we're going to have an EBS volume that's going to be made use of. So now in the context of the cloud, which and specifically in our cluster, you'll see at the bottom over there. So that means that when we are when we're deploying applications like stateful applications, then this is a situation in which your PVC, you create your PVC as part of your stateful workload, for example. The dynamic provisioning of your volumes takes place. And when that is happening, as I said, you might have an increasing number of applications that then starts to exhaust your compute resources, and Karpenter is aware of that. But and so as it starts to add more nodes to your cluster and build it out, it still takes into consideration these particular things. And bear in mind, with volume topology awareness, in the context of AWS, your EBS volumes get provisioned in a specific availability zone. So you want to make sure that you're applying, for example, a node affinity rule. And with that node affinity rule, it's for a single availability zone so that there's no reattachment issues, because pods are ephemeral. And so when that pod eventually dies, you still want it to be scheduled to in the right availability zone where it was before, so that it can easily reattach to that volume. So Karpenter also provides support for this. So great use case for this as well would be situations of stateful workloads, and you want to be able to scale those with the right kind of compute resources while supporting this kind of feature in Kubernetes. All right, so I did mention to Harry that just before getting into the demo, I was going to take a couple of questions, if any exist at this point. So Harry, I'm not sure if you want to read those questions for me or if I should just head over to the chat myself.
Yeah, I'm looking at the chat now. There aren't any questions.
Okay.
So yeah, the audience, you can raise your hand if you want to also unmute yourself, if you prefer to ask your questions like that. Or yeah, please feel free to type it in the chat. But yeah, so far we don't have any questions, so I think you can continue.
Okay. Cool.
Actually, I have one, Luke.
Yeah.
It's actually about the volume topology awareness that you're just talking about. So in a situation that you mentioned, right, with availability zone A and availability zone B, but then now your volume, is stuck in B, but then now, all of the nodes in availability zone B is full, right? So does Karpenter offer a way to remove some of the existing pods so that you can actually put the pod that is meant to be attached to volume in availability zone B? Because in that situation, like how would you actually, because that node, there's only one node in availability zone B, and the volume sits there, and this pod really needs this. So what does it do? Like, does it have to remove the existing ones and schedule the new one onto it? Or yeah, how does that work?
Yeah, great question. And that's essentially it as well, because remember, it's considering your pod's requirements and any existing constraints. And so in a situation like that, if it means rescheduling certain pods and, for example, getting a larger EC2 instance to accommodate other pods that don't have a specific constraint applied to them, then they essentially get placed on separate nodes. And it makes sure that for, like you said, we've maxed out a particular node here. So it will make sure that it's able to get an EC2 instance that meets the particular requirements for those remaining pods, for example. I hope that answers your question. Yeah,
that makes sense. Okay, thanks.
Cool. All right. Cool. Okay, let me switch over to the demo now, and then if there are any questions after that, we can definitely take them as well.
Yeah, sounds good.
All right, so I've switched over to my editor. So please just confirm that you can see VS Code.
Yes.
Great. So let me start off with the provisioner. So this is a very important part of the essentials of Karpenter. Karpenter has a controller, is essentially a controller or an operator, and it also has a custom resource definition called the provisioner. And the provisioner is what allows us to actually be able to configure the behavior around Karpenter, because you might have different constraints that you want to put in place. And so the file that we have in front of us over here is our provisioner. And under the requirements, you'll see over here that I have the option to include whether I want my compute resources that get added to be spot instances and on-demand instances, or just one of the two. And this is very helpful because there are different constraints that apply to the spot instances and the on-demand instances, and they have different implications. So this makes things a little bit more dynamic in that sense, and allowing you to still be able to accommodate certain types of EC2 instances that you want to be able to go with when you're scaling your resources. In addition to that, you can apply any certain limits around the EC2 the new instances that Karpenter provisions. So you'll see over there resources. I've got my limits set to the CPUs to 1,000, and the same thing for a memory, and the same thing for memory is also to 1,000. And then under the provider section, so under here, these are things that are specific to the AWS context. So these are essentially key value pairs. So this is how Karpenter will know how to communicate with the different resources. So the subnet selector, so it will know which subnets to essentially provision the resources in. So it will be all of those that have the specific tags. You'll see Karpenter over there .sh discovery alpha. So to look for that key value pair, look for a subnet that matches that particular key value pair, and the exact same thing with the security group selector as well. So these are things that it will take into consideration. And there are additional properties that you can add to beef out your provisioner, but just so you're aware that this is the main configuration file that you would be working with. So after you've deployed Karpenter, you would then be deploying your provisioner so that it knows how it should behave and the parameters that it should act within. Okay, so the first application that I'm going to be deploying to my EKS cluster is this inflate application, and it's the example application that you can find on a number of introductory Karpenter resources or technical articles online. And I'm going to be creating 8 replicas. I'm going to scroll down here specifically to the spec section where our container configurations usually live. And I want you to pay close attention to the affinity part. So this is, as I mentioned, how you apply the pod affinity rules are very similar to how you'd apply the node affinity rules. So where, you'd basically swap this out. And the first thing is the rule. So in this case, I'm going with the required approach. So that's how strict I want this. I want this to essentially follow a strict approach in terms of these scheduling constraints that are being applied. And then, of course, we've got our labels selector as well. You'll see there the key being app. And then very important, you'll see topology key. So this is how the particular topology that you wanted to be aware of in terms of how it applies these constraints. So in this case, I want it to be based on an availability zone. So that means that these pods that get deployed should have a strict scheduling approach to being deployed in the same availability zone. So it's not so important if they end up on the same node, as I mentioned earlier. What's important is that they should be in the same availability zone. Okay, so I'm going to switch to my terminal. And right now you should see K9S, which is just a basic open source tool for managing your cluster. And so these are the pods that I have running at this point, and you'll see all over here because it's showing all the pods in all the namespaces. So you'll see that that inflate application has not been created as yet. I'm going to switch tabs. And I'm going to create that. Oh, I think I was trying to delete instead of add. Just rid of that. There we go. All right, so let's switch back to K9S so we can see what's happening here. So you'll see a number of pods are in a pending state, slowly getting sorted out over here. And what I want to do now is switch over to all right. Oops. All right, let's go the old-fashioned way. Okay, right. So you'll see over there that we've got a new node that is being provisioned. You'll see it over there, 38 seconds, and it's not yet ready. And so that's essentially the node that Karpenter is provisioning to make sure that all of our resource requirements are met for particular workloads. And I'm going to come here to the Karpenter application and just run an L so we can see the logs in here. And let's great. So I know it might be a little bit difficult to see, but I'm going to try and focus on certain parts over here, just so you can see the process of Karpenter actually communicating. And you'll see over here, discovered 452 EC2 instance types, discovered EC2 instance types, zonal offerings, discovered the subnets, the security groups, the Kubernetes version, and then it goes to work and essentially creates a launch template, launches the instance, and created a node with 6 pods requesting these. You can see over here the CPU and the pods. So that means that Karpenter was essentially trying to make sure that all of these pods got provisioned based on and went to work to essentially make sure that the compute resources matched up to that. And we can see over here that all of them have been provisioned now. And if you were to take a look at the node IPs, you'll see 10.0.0.142. We've got 1, 2, 3, 4, 5, 6. So 6 of the inflate applications have been placed on the same EC2 instance. So that already tells us this is probably a pretty big node. So if we were to come here as well, I'm sure that now if we run it, so you'll see that this EC2 instance is ready. Just going to describe the node. Right. So let's scroll up because there's still something that we're really interested in over here. It's not just a case of them all being in the same, most of them being on the same node. So you'll notice over here that the Topology Kubernetes IO zone is EU West 1A. So the reason that Karpenter was actually provisioning such a large EC2 instance was not only to meet the pod requirements, but was to also make sure that that it also made sure that that EC2 instance was provisioned in this EU West 1A. So most of the pods should be there. And so if we were to take a look at, just so in case you want to see the EC2 instance type, you'll see over here C5A 2X large. And this is an EU West 1A. So I'm just going to clear that. I'm going to switch back here and let's look for the pods that are on a different EC2 instance. All right, so that would be this one over here. That's on the 10.0.0.5.7. All right, let me grab that. And let's see where this is in terms of the availability zone. All right, I'm going to scroll up. There we go. So remember, this is a T3 medium EC2 instance. So this should have been one of my original EC2 instances. And you'll see that this EC2 instance is an EU West 1A. So that constraint is still met. So we've covered 7 of them. And that, I'm hoping you'll go by my word over here, that we can probably trust that the pod that was, I know there's another one the one over there with 112. So that was probably also in EU West 1A. So the point is Karpenter, again, making sure that all of the pods get scheduled to an EC2 instance that's big enough to handle them. But in addition to that, with the constraint of making sure that all of these are in EU West 1A. Cool. So that's an example with pod affinity. So now I'm going to do the opposite with pod. I'm going to do this. We're going to recreate the process, but with pod anti-affinity. Cool. All right, so let's take a look at the node layout again, now that those pods are gone. Cool. All right, so this node still exists, but I think if we gave it a bit more time, Karpenter will probably get rid of that one. I'm going to run the logs over here to see what is happening. Yeah, there we go. Oops, scrolled up real quick, but you can see it over here that it actually deleted the node that had been created. And so Karpenter is also keeping things clean in that particular sense. But let's go ahead and run the example with pod anti-affinity. And before I do that, just want to switch back to my editor so you can have a quick look at the manifest file. So it's the same application. The only difference now is the constraint that we're applying. So you'll see over here pod anti-affinity, and this time I'm taking a preferred approach. So it's a little bit softer and you can apply a weighting to it. So you can see over here in this case 50. And I'm still going with the topology key of availability zone. So in this case, I want my pods to be spread out across different availability zones, but it's not a strict approach. So we might find that there's still some pods that get scheduled to nodes in the same availability zone. So switch back to the terminal and create this. All right, so we can see the pods over here are coming up. In the meantime, I'm just going to go ahead and run kubectl get nodes. Great, and you can see over here, there's a new EC2 instance that's coming up. It's not yet ready, 19, just you can see the age over there, 19 seconds.
Luke, while we're waiting,
Yes.
just wondering
Yep.
if we can answer a question that I see on chat over here from Gareth.
Yep, absolutely. Please.
Sure. So Gareth asks about Kata. So Gareth says, I'm using Kata with the SQS trigger. Do you know if Karpenter would deploy a node for each pod, or will it spawn large nodes to handle the 500 plus pods? The pods run short-lived jobs, therefore they only run for a few minutes, but there are thousands per hour. Currently, I use HPA to scale larger nodes, but I'd like Karpenter to automatically size nodes instead of manually updating the node groups. So I think the question here is, do you know if Karpenter would deploy a node for each pod, or would it spawn large nodes to handle the 500 plus pods that Gareth has running?
Yeah, so the model I've seen, and again, it's meant to be like a cost-effective model and working based on the actual requirements. Karpenter will know whether it should just be adding the same type of EC2 instance or if it should get one large one. And in many cases, I think you saw with the example that I gave, it was the, I think it was the C4 large 2x large EC2 instance. So similarly, I definitely think that that's something that you could try out. And you might recall that when I showed the provisioner configuration file, you can go with spot instances, and spot instances are good because they're essentially for short-lived workloads as well. So I definitely think that's something you can try out, even if it's just for jobs. I think Harry said that Gareth was asking about jobs, right?
Yeah. So Gareth also added that what's happening is it's a pod per SQS message. So I'm assuming that it's like, it comes fast and it goes fast.
Right. Okay. So that would be an interesting case to try out. That would, yeah, I would still test it out. And again, like this is, that's probably something you can also even bring into the Slack channel. I'd encourage you to bring that there. Try it out. I'm also keen to actually test it out. You can, if you don't mind, you can reach out to me, and then I can try and replicate an example of that. But we can also bring that same discussion to the Slack channel as well to see how that pans out.
Yeah. So I also have just an add-on question, I suppose. So with Karpenter, we saw just now like how quick that node got deleted. But in Gareth's situation, right? Let's say if pods are coming and they're going, but they're coming again. Like it's not, I would say, efficient, for Karpenter to kill the node that's already there just to spin up a new one. So is there a buffer time that we can set? Or is there like a wait time before it sees like a workload? Yeah, something like that.
Yes, yeah, and if I remember correctly, that's something I think you can configure as well in the provisioner file as well.
Okay, that's awesome.
Yeah, cool.
Okay, great.
Let me just quickly.
I forgot to ask Gareth if that answered your question.
Yeah, right. Sorry. Please let me know. All right. So just looking at a pod over here, that's in EU West 1A, and this is for 10.00.57. So that was that one over there. Now we're going to take another inflate pod. Let's just grab this one over here at the top. Okay, this one is also in EU West 1A. Just remember, we've got a preferred approach over here. So let's go with another one. So far we've checked 115 and 57. let's check 158. Lastly, we can check 112, but I'm hoping that, oh, that's a problem. Okay, well, let's see.
Because it's 01, I think, instead of 00. 10.0.
Oh, yes, right. Thank you. Good eye. Good eye. Thank you. Yeah. There we go. Cool. So you can see over here, this one has been placed in EU West 1B. So again, you can follow a strict approach if you want to have that repel effect or constraint for your pods, for the pod affinity. Maybe that was too quick for some people to see, but let me just highlight it again in case you missed it. So it's over here. That's what I was specifically looking at. See, this one is in EU West 1B, whereas the other two pods that we looked at, those replicas were in EU West 1A. Yeah, so that's essentially it. I would have loved to show you the volume topology awareness example as well, but I'm just trying to be considerate of time as well. But I do have resources showing that example, both a technical article and a video as well, in case you want to check those out.
Awesome. Yeah, thank you so much, Luke. Yeah, it's an awesome presentation and awesome demo. It's great. So we do have a few more minutes for questions. We'll start a little bit later. To the audience, if you have any questions that you would like to ask, please drop it in the chat panel and we'll address them. Or you can just raise your hand, unmute yourself, and ask Luke directly.
I can go ahead and stop sharing, right?
Question. Yeah, you can go ahead and stop sharing. Yeah, Topology, would you like to ask the question yourself, or should I read it out?
Let me try.
Okay, go ahead.
Cool. Thank you very much for the presentation, Lukonde. So just one question that I have, like, does Karpenter take like interaction frequency into consideration when you using spot instances?
That's a really good question, and I'm honestly not too sure. So that's, I'd probably have to look into that one as well. And I think that's actually definitely worth dropping as well in that Slack channel. But that's a great point. It's kind of why I try to go with a combination of both spot and on demand. So that's a really good, really useful.
Cool, thank you very much.
Sure.
So excuse the background. So the second question that I had is, the second question that I had is, like, is it possible to get like best of both worlds, and like when using spot and on demand based on percentage split? Like, for instance, if you have like 6 nodes and say I want my my provisioner to spit up 2 spot instances, or like 4 on-demand nodes.
Yeah, great. At this point, I don't think there is. I know that the default is on demand, and you can add spot as well. But in terms of an actual percentage split, I'm not aware of that particular feature.
Thank you.
Really good questions though, Toba. Like, so I'm not just advertising this for free, but I really think these are the kind of things that will make this an even better tool. So I really hope that you can bring these over to the Slack channel, because the builders, and the builders include anyone that gets involved in the ecosystem or the community, we're the ones that are going to make it out to be what we want it to be. So I think questions like this are excellent to improve it.
100%. Thanks. Will do.
Sure.
Yeah. And I think the community always welcome specific use cases, because these are actual people using them a specific way.
Yes.
So of course, the builders want to know what is what is required, what is needed. So please do utilize the Slack channel and ask as much as you can. And it's always cool to look at these specific use cases, because I think this is going to be a good replacement for the good old cluster autoscaler. So I actually have a question about that. So if we have Karpenter inside our cluster, does that conflict with the existing cluster autoscaler? So we have to choose one or the other, right?
Yeah, that's a great question. So it's recommended that you go with one, just one of the two, because they're essentially both changing the compute resources for your cluster. So you don't want to run into any conflicting issues over there. Granted, cluster autoscaler kind of works with, the more of like that node group approach. But some of the, the restrictions that cluster autoscaler introduces are the same things that Karpenter is trying to solve. So to avoid running into issues like that, it's kind of advised that you go with one of them. I haven't heard anyone say, never run both, but it's definitely advised to just pick one of the two. And there is a video online as well about how to migrate from cluster autoscaler to Karpenter, which is pretty useful as well. So you can check that out.
Cool. Awesome. Thanks, Luke.
Yeah.
So Clive is asking if we can share the link to the Slack channel. Is that just the CNCF Slack channel where the Karpenter works?
No, so this is actually specifically the Kubernetes Slack workspace.
Okay, cool.
Yep.
I see Ronaldo already pasted.
Oh, great.
Cool.
Yeah, so you'll find the Karpenter channel there.
Cool. So, yeah, Luke, again, thank you so much for doing the presentation, giving the talk. It is great content. I think we all learned a lot. And just a token of our appreciation, JetBrains, our sponsor, has also kindly given you a license. So I don't know if you use JetBrains product, their IDE. I remember you used to, but there will be a license coming your way. You can admit it's fine.
Awesome. Yeah, no, that's cool.
No, so they are a sponsor. We love them. That's awesome. Great, cool.
Yeah, no,
so again, thank you so much. And just an ending note, we are always looking for speakers to come and share with us their cloud native journey. So please reach out to me if you are interested in becoming a speaker. You don't have to go and talk about some like super technical content. We always love talking about use cases, how people implement some of the projects out there. Like, how do you actually use it in real life? How do you actually use it in your organization? So that's the type of story that we're always looking for. So thanks for joining us today. The webinar recording and slides will be online over the next 2 days. I'm actually not sure. I actually didn't ask you, Luke. Will you be able to share the slides? Or
yes, yep. I will, I think.
Perfect.
Yeah, definitely. Yeah.
Okay, great. And yeah, thanks everyone. We're looking forward to seeing you at next month's CNCJ meetup. Have a great day.